Welcome AP Stat students to my favorite chapter, Chapter 6. The reason I like it is because Chapter 6 is all about probability. So if you like game theory, then you will like probability. All right, so first thing we're going to talk about is just the idea of probability. For many centuries, humans thought that random events were controlled by supernatural beings, by the gods or by God. They thought it was out of their hands. They would roll the bones, and whatever the bones landed on, that was a supernatural being's will. Okay. Nowadays, we know that yes, it's a random event, and we cannot predict. If I flip this coin right here, we cannot predict what it will land on the very next flip. But we realized if we keep track of many flips of this coin, over millions and millions of flips, that we're going to get roughly half to land on each side. Okay, and that's the idea of probability. It's not that I can predict the very next outcome of a random event. It's that over many trials of some random phenomenon, I can predict the distribution of outcomes. Okay. So just to hammer this home, first of all, I need independence. So, for example, the coin, every time I flip it, it needs to be a new flip that's independent of the result of the last flip. And that's why I use a coin or a die to talk about this, because we know if I roll this die and then I pick it up and I'm ready to roll it again, well, whatever it landed on the last roll has no impact on the next roll. Okay, but be careful. Things like cards, when you deal cards from a deck, right, you're not replacing the card. So now you have something that is not independent, right? Every time you remove a card from that deck of cards, you've changed what's left in the deck. So you've changed the ongoing probability. Okay, that's called conditional probability. But we're starting off right now. The general idea of probability, we need independent trials. So flip this coin over and over again. Each flip would be independent. Okay, and this initial idea is what we call an empirical idea. We do it many times. We keep track of the results, and we end up with a ratio. Just like last chapter, that's why we ended chapter 5 with simulations, because we would do something over and over again, and we would simply keep track of the results. So the numerator is how many times our event occurred, and the denominator is how many trials we ran. And that gives us a fraction, and that fraction is the empirical probability. So when I ask you about this coin and I say, well, what's the probability it lands on heads when I flip it? And you say 50%. It's not because you have flipped this coin many times and kept track of the results. That would be the empirical approach. Okay, it's because you would be using what we call the classical or theoretical approach, which we'll get to in a minute. Okay, so here we go. The classical approach. Okay. Under the classical approach or theoretical approach, we assume that we could count or list out all the possible outcomes of our random phenomenon. Okay, we call that the sample space. So that's why I'm talking about a coin. It's very simple, right? There's two outcomes, heads and tails. And so we can count both of those. And then we can count the number of ways whatever we're interested in can occur. So with my coin, there's two sides, and if I'm interested in getting heads, well, that's 1 out of 2. Okay, I didn't actually flip the coin a million times and keep track. I used the theoretical approach. I just simply counted. Okay, so under the theoretical approach, it's the number of ways my event can occur divided by the size of the sample space, or in other words, the total number of possible outcomes. So we can apply the same logic to a die. Let's say I want to roll, I'm playing a game, and I really want to roll a 6. If I roll a 6, I can win the game. Well, this die has 6 sides. So the theoretical approach would tell me I have a 1 out of 6 chance of rolling that 6. just a side note, by the way, if you use these cheap dice from a Monopoly game, for example, the little black circles, those are called pips. And you can see these pips have been cupped out or hollowed out, which actually makes this side the lightest side. And on the other side of the die is the heaviest side. So on a die that hasn't been weighted correctly and has cupped out pips, it will land on 6 more often, and it will land on 1 the least often. Fun experiment. Get a die like this and roll it a few million times and keep track of the distribution. Hey! That's why casinos, you'll see they're always putting in fresh dice. They test them regularly to make sure they're balanced perfectly evenly. Otherwise, people could take advantage, right? So anyway, here's the problem with theoretical probability. Counting. I know it doesn't sound very, very difficult, but counting can become extremely difficult. You must count everything exactly once. It's easy to leave an outcome or more than one outcome out of your count. It's also sometimes easy to double count or even triple or quadruple count an outcome in your sample space. So counting is the challenge with the classical or theoretical approach. And I will illustrate that in a little bit. Okay, so under both of our definitions of probability, the empirical or the theoretical, okay, we realize that the lowest probability I could ever get is 0, right? I can't observe an outcome a negative number of times, right? 0 is the lowest I could get, okay? And on the other side of the coin, right, I cannot observe an outcome, right? There aren't more ways for it to occur than there are outcomes in the sample space, right? So 0 is the lowest possible probability and 1 is the greatest possible probability, which is great. It means all of your answers must be between 0 and 1 inclusive. That should really help you out, right? Please don't be the student. There's always one every year or even more than one. They give me a probability greater than 1. So if that happens, you've miscalculated, you've miscounted, something went wrong. Please don't be that student. All right, so now let's take a look. Here is an example. Let's say that I'm able to throw a dart at a dartboard. And let's say the dartboard, we'll call the dead center of it the point 0, 0, the origin. And then let's say that our dartboard has a radius of 4 units, whatever, inches, feet, miles, doesn't matter, units. Now, let's assume that I am able to throw the dart at the board completely randomly. And every point has an equal chance of being hit by my dart. Okay? So what's the probability? Again, I'm throwing the dart randomly. I'm not trying to hit the origin, right? What's the probability that the dart lands right on the origin? Okay, so pause the video for a second and think about that. See if you can come up with an answer. Okay, so let's draw this scenario. So let's say that's 4, -4, looks like 4, and -4. Not very round circle, but pretend. So there we go. Let's say that's my dartboard. So I'm basically picking a random point, ordered pair point, from inside this circle. And the question is, well, what's the probability the point picked is the point 0, 0? Well, the empirical way of doing this is not going to work out because none of us as humans can throw a dart completely randomly and make sure that every point on the dartboard is equally likely to be hit. So that's not really going to work. And the other problem is if I try the theoretical approach, counting is a huge problem, right? So the origin, right, that's 1 point. So the origin, that's the point 0, 0, and that's the only point on the dartboard that's the origin. So there's one of those. But how many points are there on a dartboard with a radius of 4? Okay. Well, this circle contains an infinite number of points. And I want one of them. So there's only one origin out of an infinite number of points. By the way, just an aside, I always love this in calculus. If we think about it, well, I'll get back to it in a second. So anyway, the origin is 1 point out of an infinite number of points. Okay, so the probability, if you randomly select, is 1 over infinity, right? Okay, well, what is 1 over infinity, right? For some of you, you've kind of done limits and calculus, and that might make more sense than others, but this concept of infinity, the denominator is infinitely large. It goes and goes and goes and goes and goes. So 1 divided by infinity, it's technically not 0, but it gets infinitely close to 0, right? So we're going to say that the probability of hitting the origin is basically 0, even though technically it's not 0, okay? So just pointing this out, and again, this is the problem with counting, right? There are times when I would say the probability of something occurring is 0 when it actually could occur, right? That was my example here. So this actually can occur, but we would assign it a probability of 0. So kind of tricky, fun stuff. Okay, and then of course it can go the other way around too, right? I could come up with an event that ends up with a probability of 1 that isn't guaranteed to occur, the complement of what I just said. What's the probability the dart does not land on the origin? Right? Again, I can't do that empirically, and I can't count it theoretically. I have to use a little logic, a little common sense. Okay. All right. Now, here's more of a question that I would ask on the test, right? What's the probability my dart lands in a bullseye region of my dartboard? So let's say this is my bullseye region. Okay. Now, again, we have an issue with counting, right? My dartboard has an infinite number of points in it. My bullseye region also has an infinite number of points in it. So if you just go, oh, I'm going to count, well, infinity divided by infinity, right? That doesn't get me an answer. So again, pause the video for a moment and see if you can come up with a way to answer this question. Okay. All right, hopefully you realized that we could think in terms of areas, right? Both have an infinite number of points, but the dartboard has a bigger infinity than the bullseye's infinity. So what we want to do is think about the area of each. So the area of the bullseye, right? It's a circle, pi r squared. Well, r is 1, so this has got an area of pi, right? And then we're going to divide that by the area of the dartboard. Okay, well, the area of the dartboard, again, pi r squared, so pi times 4 squared, or 4 pi squared, or sorry, 4 squared pi. Well, the pi's cancel out, and we would have a 1 in 16 chance of picking a point from the bullseye region if a point were randomly picked off of this dartboard. So again, we didn't do it empirically, and we didn't count everything from a sample space, right? We used a little knowledge that we have of geometry to answer this question. So whenever counting becomes a huge issue, try to think maybe in terms of something else like area. And that's what I wanted to talk about real quick, calculus. I was always fascinated that a single point has no area, right? A single point has no area. But if I put an infinite number of these non-area points together, I now somehow have area. That always just blew my mind. Okay. Just like a line, right? A line has no area because it has no width, right? So here we go. All right. Now, you will get lots of questions that involve dice, coins, and cards. So let me go over, I think everyone understands a coin has two sides. It's, pretty simple, heads and tails. And most people understand that a standard die has 6 sides. But some of you may not have played cards. So let me go over the contents of a standard deck of cards. Okay, the standard deck of cards is made up of 4 suits. You have your clubs and spades. Those are your black suits. You have diamonds and hearts. Those are colored red. Okay, within each suit, you have 13 cards, the same 13. And those 13 cards are ace, king, queen, jack, and then cards with numbers on them. And then the numbers are 2, 3, 4, 5, 6, 7, 8, 9, 10. And that makes up your 13 cards in each suit. So that tells you 13 cards per suit, 4 suits. That means a standard deck has 52 cards in it. So anytime they talk about a standard deck, there's your sample space, 52 cards. And there they are, listed out, all 52. Now, you might encounter a question that talks about face cards or picture cards. Okay, face cards or picture cards are the king, queen, and jack, because these cards have a picture of a king, queen, or jack's face on them. Again, standard deck, right? We're not talking about, your SpongeBob SquarePants deck that has, Squidward and everybody on there's a picture on every card. We're talking about a standard deck, okay? Oh, so how many picture cards would there be? 4 kings, 4 queens, and 4 jacks. So there are 12 picture cards in a deck. All right, so let's practice a very simple question. Let's say I take a thoroughly shuffled standard deck of cards and we randomly pick a card. First question, what is the probability I get a red card? Okay, well, this is where I could do this empirically, right? I could shuffle a deck, take a card out, write down what I get, repeat millions of times. Or this is an example where the theoretical comes into play, much easier. So I ask myself, how many red cards are there? Well, there's 13 diamonds and 13 hearts. There are 26 red cards. And the sample space, a standard deck, has 52 cards. So there you go. There's your chances of getting a red card. Okay, you could reduce to 1/2 if you wish. I wouldn't mark 26 out of 52 wrong, though, if it's a test question. Okay? And again, we didn't actually do this, right? This is what we call theoretical. Okay, next question. Again, take one card at random from a standard deck. What's the probability I get a red jack? A red jack. You might see this written with an intersection sign like that. Red jack means that the card must be red and a jack, right? Well, there are 2 red jacks, jack of diamonds, jack of hearts. So that's 2 out of 52. Again, reduce if you feel like it. There you go. That's the chance of drawing a red jack. All right, again, same scenario. What's the probability the card I draw is a red face card? Again, this would be an intersection, red and face card. Okay, well, how many red face cards are there? Well, there's 2 red jacks, there's 2 more red queens, and 2 more red kings. So there are 6 of them. Okay, again, reduce if you wish. There you go. Chances of drawing a red face card, 3 out of 26. All right, now this last one, what's the probability I get a red card or I get a jack? Okay, this is a union, right? Or is union. So red card, union, jack. All right, so a lot of students will start by saying, okay, there's 26 red cards. I know that. And then, there's 4 jacks. And they'll do that. 26 plus 4, counting all the red cards and all the jacks. But realize, when students do that, their counting is wrong, right? because they've double counted the red jacks. There's 2 red jacks, right? Jack of diamonds, jack of hearts in here. There's 2 red jacks, jack of diamonds, jack of hearts in here. We've counted the same cards twice. So if you take this approach, you better subtract away the 2 red jacks that you double counted, right? So there's my answer. Okay. Now, other students would say, well, I'll just count up all the red cards, 26 of them, and then I'll add the jacks that I haven't counted, right? So then I'll add the black jacks. So all the red cards plus the black jacks. That also works. You could start with all the jacks plus the red cards that aren't jacks. That would start with, start with all the jacks, and then, add all the red cards that aren't jacks. That's another way to do it. Okay, so just make sure you count everything exactly once. All right, let's talk about some coin problems now. Let's say I flip a fair coin twice. What's the probability of the various outcomes? Okay, so, all right, sorry for the interruption there. My wonderful Apple device ran out of storage mid-video, so I'm not quite sure how this will cut and paste together, but I was on this problem when I ran out of storage. So here we go. We're going to go to a coin question. Let's say I flip a fair coin twice. Let's start by making a sample space. So my sample space is a listing of every possible outcome. So I flip it twice. I could get heads both times. Heads first time, heads second time. I could get heads the first time and tails on the second flip. I could get tails on the first flip, heads on the second. Or I could get tails followed by tails. And that's it. Those are the only possible outcomes in my sample space of flipping a fair coin twice. Okay, now that I have my sample space, I can count real quick. There's 4 outcomes there. That's easy. And now I can answer whatever questions they ask. So what's the probability I get 2 tails? That's right here. That's 1 out of 4. Okay. What's the probability I get 2 heads? Right here. 1 out of 4. Easy. Okay. Now, what's the probability I get 1 of each? 1 of each. Now, students will ask questions about order. Does order matter? Does order not matter? Let me make it real clear. In a sample space, order always matters. Because I could say, hey, I'll give you $1 million if you flip heads followed by tails, but you're going to pay me $500,000 if you flip tails followed by heads, right? These are 2 different things that we can keep track of, so they are different, recorded as 2 different outcomes in my sample space. Now, the real question is the wording of the problem. In the wording of my problem, does the order matter? If I say I'm happy with 1 of each, well, that's 1 of each, and that's also 1 of each. So 2 out of 4 would fulfill 1 of each. Again, reduce if you want. Okay. But again, you have to read the problem. It's the problem that tells you which outcomes will suffice based on the wording of the problem. All right. What are the chances I get 2 of the same? Okay, 2 of the same. Well, heads followed by heads, that's the same. Tails followed by tails, that's the same. So both of those outcomes fulfill the wording of 2 of the same. So there you go. And of course, on a test, if you come ask me, does order matter? I'm not going to be able to answer that. That's the whole point of the problem. Read, and you determine if the order matters or not. Okay? Does the order matter in the question, not in the sample space? It always matters in the sample space. All right. Let's try something with dice. We're going to roll 2 standard 6-sided dice. Oh, look at that. I rolled a 12, double 6s. Okay, so like you're playing Monopoly. So when I roll these, what's the chances that I roll a 7? So in other words, something like that, right? That would be a 7. So pause the video now and see if you can figure that out. Okay. All right, next question. What's the probability I roll the dice and I get a total that's even, like that, 10. Again, pause the video, see if you can answer it. Okay, next question. Again, roll 2 dice. What's the probability? I'm going to cheat. There it is. Exactly one of them shows the number 4. Okay, pause the video, answer that one. Okay, and last question, I roll the dice. What's the probability at least one shows the number 4? Okay, so I'm going to help you out. This, a lot of students try to do this by just counting things in their fingers or in their head or whatever. And I will see students stare at this problem for a long, long time. Well, could I make a sample space? I know the problem didn't tell me to make a sample space, but could I? Sure I can. So I did. There you go. There's all the possible outcomes, right? 1 plus 1, 1 plus 2, blah, 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 blah. So on, 36 outcomes. By the way, could I have figured out there were 36 outcomes without listing them all out? Yes, I can, right? There are 6 outcomes for one die, 6 outcomes for the other die. So 6 times 6, I know there must be 36 outcomes, right? That's the fundamental counting principle. And I have them all here in my sample space. So that's a nice thing to know. The fundamental counting principle allows you to know how many items are in the sample space. Then when you make your sample space, you know you've got them all listed. All right, so what's the probability I get a total of 7? Well, there's 7, there's 7, there's 7, there's 7, there's 7, and there's 7. So 1, 2, 3, 4, 5, 6 out of 36. Again, reduce if you wish. What's the probability my total is an even number? Well, that one's pretty common sense. I'm not going to circle all the even outcomes, but you can see it's exactly half of them. Or 1/2. Okay, what's the probability exactly one die shows the number 4? Exactly one die shows the number 4. So let's see. That one, that one, that one. Oh, not that one. There's 2 showing the number 4. That one, there, 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 and there, right? So count those up. That would be counting that up, I've got 3, 4, 5, and 5 more. 10 out of 36. Okay. Now, what's the probability at least one die shows the number 4? At least one. Well, all of those have at least one, but now double fours suffice. The wording has changed. Double fours, that contains at least one 4. Okay. So probability at least 1, 4 is now 11 out of 36. Okay. And a lot of my students miss that who don't make the sample space. They go, oh, okay, well, there's 6 on one, 6 on the other, so they go 12, right? But what they've done is 6 plus 6, they've double counted an outcome. Okay. And same thing with the exactly 1, 4. Sometimes people count the double 4, so they say 11. Sometimes they double count the double 4 and say 12 out of 36. So again, the sample space is super, super helpful. So I personally will make a sample space anytime the sample space isn't unreasonably large, right? So if I say, roll like playing Yahtzee and I'm rolling a whole bunch of dice, now it becomes unreasonably large. And I'll have to just do it without actually listing out the sample space. Oh, and just a side note, these cheap dice that we have here, the black circles are called pips. I don't know if you can see this, but on a cheap die, the pip will be cupped out, hollowed out, and then painted. Well, the problem with that is there's 6 cupped out pips on this side. There's only 1 on this side, which means this die is not evenly weighted. this side's the heaviest, and on the opposite side is the lightest side. So a cheap die like this will actually land on 6 more than 1 out of 6, right? And it'll land on 1, the least frequency. And that's why if you go to casinos, you'll see they don't have hollowed out pips like this. And they are constantly checking their dice to make sure that they are evenly weighted. Otherwise, of course, a player could have an advantage. And that's why they also, anytime a die leaves the table, they remove it from play because they don't want somebody to switch out the dice on them. Fun stuff. Okay, here's a question. Every year I would ask this as an extra credit question and give students the remainder of the period to try to solve it. But, you're not in my class and you could just, I'm sure, Google the answer. So no extra credit. But this is a fun question if you want to just kind of think about it on your own. Let's say the chess club, by the way, join chess club. We are looking for more members. We meet every Wednesday. Use my office hour link Wednesdays at lunch. So let's say my wonderful chess club, greatest club on campus, is having a gift exchange for the holidays. And all 7 members in the chess club participate. So they all bring a gift. And then I just grab those 7 gifts and I pass them out randomly. But I do make sure one very important thing. I make sure nobody gets the gift that they brought in, because that's no fun to open a gift. You already know what's wrapped up in that gift, right? You want a surprise. So how many different ways could I randomly pass back those gifts, making sure nobody got the gift that he or she brought in? Feel free to think about that. Try to answer it on your own. It's a fun little problem. This is way beyond the scope of our class, though. I wouldn't actually ask something this difficult on the test. But if you're like me, you come across a question like this and you find it to be very interesting. All right. That is the first lesson in probability. I hope you enjoyed it.